Hello everybody, my name's Iman. Welcome back to my YouTube channel. Today we're going to be tackling a practice problem set that relates to our lecture on atomic structure. Here we're going to build on our knowledge of quantum numbers and electron configuration. We're going to attempt problems that are a bit of exceptions to some of our rules so that we can further our understanding. So let's go ahead and get started with this first problem. This first problem says, which of the following is the correct electron configuration for zinc 2+. So if you remember from lecture, electron configuration is a representation of the distribution of electrons among the various orbitals of an atom. And this concept is really crucial for understanding a lot of the properties and behaviors of elements. Now, to determine the correct electron configuration for zinc 2+, we actually first have to determine the electron configuration of just neutral zinc atom, and then we'll talk about how we adjust it to account for the loss of electrons in this ion. Now, if we look at the periodic table of elements, zinc is right here. Zinc has an atomic number of 30, which means neutral zinc atom has 30 electrons. Now, the electron configuration of neutral zinc atom, it follows the order that's prescribed by the Aufbau principle, the Pauli exclusion principle, and Hund's rule. According to these rules, electrons fill orbitals starting from the lowest energy level to higher energy levels. And the filling of orbitals can be remembered from the sequence we discussed in lecture: 1s followed by 2s, then 2p, then 3s, then 3p, then 4s, then 3d, and so on. But we can also just read it straight off of the periodic table when we know that this right here, this is the S block. This is right here the P block. This is the D block. And this is the F block. So keeping that in mind, we can just read the electron configuration straight off of the periodic table. So let's do that for neutral zinc. Let's try to read off what the electron configuration would be. So we start here, and also remember that these are 1, 2, 3. These rows are numbered, and that's going to help guide us as well. So we start right here, 1s, 1s2. This is filled. Then we go over here, 2s2, that's filled. Then we make it over here. This is the 2p, 2p1, 2, 3, 4, 5, 6. This is filled, 2p6, 3s2. And then we make it over here, 3p1, 2, 3, 4, 5, 6, 3p6, then 4s2, and then 3d1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is filled, 3d10. All right, so now we just put it together, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. This is the electron configuration for neutral zinc atom. Now here, the 4s orbital is filled before the 3d orbital, even though it is at a higher principal quantum number, and that's because it's lower in energy when it is unoccupied. Now, when zinc forms this zinc 2+, which is what the problem is asking for, the electron configuration of zinc 2+, not neutral zinc, it loses 2 electrons to form this 2+ cation. Where are these electrons removed from? These electrons, they're going to be removed from the 4s orbital first, not the 3d orbital, despite the fact that the 4s orbital was filled before the 3d orbital in the neutral atom. Why? This is because once that 4s orbital is occupied, its energy becomes slightly higher than that of the 3d orbital. Additionally, in this cation state, the 3d electrons, they experience a greater effective nuclear charge, which makes them more tightly bound to the nucleus compared to the 4s electrons. So it would actually be harder to remove 2 electrons from the 3d orbital than it would be to remove it from the 4s. All right, now here is a trick to keep in mind. All right, So for positively charged ions, where do you remove the electrons? What's something to keep in mind when you're attempting similar problems to this? Always start with the neutral atom and then remove electrons from the subshells with the highest value for N first. All right. In the case that there's multiple subshells that are tied for the highest N value, then electrons will be removed from the subshell with the highest L value among them. So keep that in mind. And so then considering all that, we're going to be removing the 2 electrons from the 4s2 orbital. And again, also just to fall back on some concepts we discussed in lecture, all right, having a half-filled or fully filled orbitals, especially for the d orbitals here, it's going to have lower energies, higher stability than other states. Here, a full d shell outweighs the cost of moving an electron out of that 4s subshell. And so then, our electron configuration for zinc 2+, it's going to be 1s2, 2s2, 2p6, 3s2, 3p6. We're going to remove those electrons from the 4s, so 4s, 0, no electrons there, 3d10. This is the electron configuration for zinc 2+. Now, if we go back to our answer choices, the answer choice that aligns exactly with that is going to be answer choice A. All right, so for problem number 1, the correct answer is A. Wonderful. Let's move on to problem 2. Problem 2 reads, which of the following quantum number sets is possible? So let's refresh our minds on quantum numbers and their rules. Quantum numbers describe the properties of atomic orbitals and the properties of electrons in those orbitals. And we have 4 quantum numbers. The first one is the principal quantum number, denoted by N. This indicates the energy level and the size of the orbital. It can take on any positive integer value, 1, 2, 3, so on. Then we have the angular momentum quantum number, denoted L. This describes the shape of the orbital, and it values in range from 0 to n-1, all right, for each principal quantum number. Now, each value of L, it corresponds to a different type of orbital. So when L equals 0, we're talking about the s orbital. When L equals 1, we're talking about the p orbital. When L equals 2, d orbital. And then when L equals 3, f orbital. Then we have our magnetic quantum number. This describes the orientation of the orbital in space, and its values range from -L to positive L for each value of L. And then last, we have our spin quantum number. This describes the spin of the electron. It can only have 2 possible values, +1/2 or -1/2. Now, to determine whether a set of quantum numbers is possible, we're going to have to check if the values of N, L, ML, and MS are consistent with the rules above. So we're going to go through each one by one and see if each quantum number set given to us by the answer choices makes sense or not. So let's start with A. Here we have for N is equal to 2. This is a positive integer, so very much possible that N equals 2. Then we have that L also equals 2. Now let's remind ourselves that the rule for L is that it's integers from 0 to n-1. So actually when N equals 2, L can only be 0 or 1. So this is not possible for N to be equal to 2 and then L to also be equal to 2. This quantum number set is not possible. So A is not the answer choice here. All right, let's move on to B. Let's see if B is a possible set. For B, we have N equals 2. All right, this is possible. L equals 1 here. Okay, this is good. Remember, for N equals 2, L can be either 0 or 1. So this is very much possible. L equals 1 here. Now, for ML value, it's -1. Is that possible or not? So our rules for the magnetic quantum number is that it's integers from -L to positive L for each value of L. Our L value is 1. So that means our ML value can be -1, 0, or +1. In that set, it says that ML is -1. That is very much possible. And then our MS value is +1/2. That's a value that is allowed for this MS quantity. All right, so answer choice B is a quantum number set that is very much possible. Let's still work through all the other answer choices as well, because this is good practice. So let's do C next. For C, N is again equal to 2, so that means L can only be 0 or 1, and here L is actually 0. So this is very much possible. So far, so good. Now, if L is equal to 0, there's only one possible value for ML here, and that is just 0. But we're given here that ML is -1. This is incorrect. When L is equal to 0, the only possible value for ML is 0. So this is a quantum number set that is not possible. Last but not least, let's work through D. D says that N is equal to 2. So far, so good. L is equal to 0. Okay, also good. And here, ML is equal to 1. Again, this is not possible. When L is equal to 0, the only possible value for ML is 0. So this is another quantum number set that is not possible. The only one that is correct is going to be answer choice B. So 2 is B. Let's go ahead and move into problem 3. Problem 3 reads, what is the maximum number of electrons allowed in a single atomic energy level in terms of the principal quantum number? So for this problem, we had discussed in lecture what the answer would be. We said that for any value of n, there will be a maximum of 2n squared electrons. That is 2 per orbital. But let's say that's a piece of information you forget in the middle of the exam, right? How can we work through the information we know about quantum numbers to reach that relationship anyway? So that's what we want to cover in solving this problem. Now, to determine the maximum number of electrons that can be accommodated in a single atomic energy level, we need to understand how electrons are arranged in orbitals within each energy level. And if you remember the principal quantum number, this indicates the energy level of an electron in an atom, and each energy level, it can contain a certain number of subshells, which are designated by the angular momentum quantum number. So let's work through this together. We're going to scroll up here to some free space and do this together. So let's say for n equals 1, all right, for n equals 1, we only have one subshell, right? Because L can only equal 0. This means that we only have one subshell, which is that S subshell. Okay, when n equals 2, L can be either 0, which is that S subshell, or L can also be 1, which relates to that P subshell. Wonderful. And then when n equals 3, our L value can be 0, which relates to our S subshell. It can be 1, which relates to our P subshell, or it can be 2, which relates to our D subshell. Okay, now each subshell consists of a certain number of orbitals, and each orbital can hold a maximum of 2 electrons. We can determine how many orbitals are in each subshell and for each given energy level. So let's work with this information we have, and we can tell the number of orbitals we have from the magnetic quantum number, right? Because the magnetic quantum number, it can take on values from -L to +L, including 0. And all those values tell us is the number of orbitals we can have. So for n equals 1, we only have the S subshell because L can only be 0. When L is equal to 0, ML can only be 0, which means that there's only one orientation for the S subshell, which means we only have one orbital here. And with one orbital, we can only house 2 electrons. Okay, when N is equal to 2, L can equal 0 or L can equal 1. When L equals 0, ML can only be 0, which means that there's only one orbital in that 2s subshell, which can house only 2 electrons. But when L is equal to 1, we're talking about that p subshell. That means ML can be -1, 0, or +1. That is 3 different orientations that ML is telling us. That means in that p subshell, we have 3 orbitals, each of which can house 2 electrons for a total of 6 electrons here. Okay, then when N equals 3, L can equal 0. When L equals 0, ML can only be 0, so there's only one orbital here that can house 2 electrons tops. When L is equal to 1, that's that p subshell, ML can have 3 total orbitals, just like we worked over here, which is a total of 6 electrons. And then when L is equal to 2, ML can be -2, -1, 0, 1, or 2. This is 5 orbitals that are housed in the 3D subshell. And that means for these 5 orbitals, we can have a total of 10 electrons. Okay, let's write this out a little more clearly and then see what the mathematical relationship is. So our conclusions from all of this information is that when N equals 1, there's only one total orbital that can have 2 electrons. When N is equal to 2, we actually have one s orbital, 3 p orbitals for a total of 4 orbitals, all right? And that gives us a total of 8 electrons. Wonderful. And then for N equals 3, we have one s orbital, 3 p orbitals, 5 d orbitals for a total of 9 orbitals in the N equals 3 energy shell. And that gives us a total of 18 electrons. Now, since looking at this first part right here, all right, for each value of N, we have some number of orbitals. What is the mathematical relationship here? In general, the total number of orbitals in the nth energy level is just n squared. For n equals 1, we have 1 orbital. 1 squared is 1. For n equals 2, we have 4 orbitals. 2 squared is equal to 4. For n equals 3, we have 9 orbitals. 3 squared is 9. So our relationship between the number of orbitals to the nth energy level is just n squared. But that's not what this problem is asking. This problem is asking us, what is the maximum number of electrons allowed in a single atomic energy level in terms of the principal quantum number? Now we have to remember, all right, and now we have to consider this part. Each orbital can hold a maximum of 2 electrons. That's how we got these numbers, just by multiplying the orbitals by 2. And so we can find this new equation by just taking n squared and multiplying it by 2, where 2 accounts for the maximum of 2 electrons that each orbital can house. And so the maximum number of electrons is going to be 2n squared. The answer to problem 3 is going to be C. Now we can move on to problem 4. Problem 4 reads, which of the following equations describe the maximum number of electrons that can fill a subshell? All right, so this answer is going to be in terms of L, the angular momentum quantum number. So to determine the maximum number of electrons that can fill a subshell, we need to understand the relationship between the angular momentum quantum number and the number of orbitals in that subshell. Remember, each subshell corresponds to a specific value of L, and contains a set number of orbitals, each of which can hold a maximum of 2 electrons. And actually, we're kind of going to piggyback off of some of the information we talked about from problem 3 because it's going to help us here. So what we're actually going to do is we're going to make a table to simplify some of the information we just covered and then work through this problem. So what we're going to have in this table is 4 columns. All right, this one is going to be for subshell. This one's going to be for our L value. This is going to be for orbitals, number of orbitals here, number of orbitals. And then here, we're going to have number of electrons. Okay, so for the subshell S, our L value is going to be 0, which means our ML can only be 0, one value, which means there's only one orbital here. And if there's only one orbital, then we have a total of 2 electrons. Now, for the p orbital, for the p subshell, the quantum number is going to be equal to 1, which means that ML can be -1, 0, or +1, and tells us that we have 3 orbitals here for a total of 6 electrons. Then for our d subshell, our L value is going to be 2. And if L is 2, ML can be -2, -1, 0, +1, and +2, which tells us that's 5 values. We have 5 orbitals here. And in 5 orbitals, we can fill 10 electrons. Okay, now knowing that, all right, let's remember that for a given subshell, the number of orbitals is determined by the range of ML values. So what is this relationship between these two numbers right here, L and the number of orbitals? How can we relate these to each other? Now, we did talk about this expression, but even if you don't know it, you can work backwards by figuring out what this relationship between these values are. The relationship is going to be 2L plus 1. So when L is equal to 0, all right, when L is equal to 0, this equation is going to give us a value of 1. When L is equal to 1, this equation gives us a value of 3. When L is equal to 2, this gives us a value of 5. So that matches up. Now we have a relationship between L and the number of orbitals. But we're not done just yet. That's not what the problem is asking us. There's just one more step. It's asking which of the following equations describes the maximum number of electrons that can fill a subshell. So now we know a relationship that tells us the number of orbitals. And then we need one more step to go from orbitals to number of electrons. We know each orbital houses only 2 electrons. So we can take this expression, 2L plus 1, and multiply it by 2. Then we can distribute the 2, all right, to get our new expression 4L plus 2. This is the equation we're looking for, and that makes the correct answer for 4B. Wonderful, so that's 4. Let's move on to problem 5. Problem 5 says, which of the following atoms only has paired electrons in its ground state? In the ground state, atoms have electrons that are arranged in the lowest possible energy orbitals. Electrons fill these orbitals according to the Aufbau principle, the Pauli exclusion principle, and Hund's rules. And I just want to go over them because they're really important to know. Aufbau's principle says electrons fill orbitals starting from the lowest energy level. Pauli exclusion principle says no 2 electrons in an atom can have the same set of 4 quantum numbers, and so that means each orbital can hold a maximum of 2 electrons with opposite spins. And then Hund's rule says electrons will fill degenerate orbitals, so these are orbitals with the same energy, singly as far as possible before pairing up. Now, when we say paired electrons, we're talking about electrons occupying the same orbital with opposite spins. And when we talk about unpaired electrons, we're referring to electrons that are occupying an orbital alone. for this problem, to determine which atom has only paired electrons in its ground state, we're just going to have to examine the electron configuration for each of these atoms that were given in our answer choices and see which one has a full orbital, all right, all fulfilled orbitals to say that this atom only has paired electrons. So let's start with our first answer choice, which is sodium. Sodium is right here. So let's determine the electron configuration by, again, just reading it off of the periodic table. So what we have here is 1s2, 2s2, 2p6, 3s1. All right, so our electron configuration for sodium is 1s2, 2s2, 2p6, 3s1. So what you notice here in this 3s orbital is that sodium actually has one unpaired electron in the 3s orbital. So it doesn't have only paired electrons in its ground state. So sodium is not the correct answer. All right, next up is iron. So let's erase this really quickly and identify where iron is on the periodic table. It is right here. So let's figure out the electron configuration. We have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d1, 2, 3, 4, 5, 6, 3d6. 3d6. Okay, so let's put this all together for iron. Iron is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d6. This d orbital, it has unpaired electrons here. Iron has unpaired electrons in the 3d orbital. Let me actually show you visually, right? Our d orbital has, or our d subshell has 5 orbitals, 1, 2, 3, 4, 5, and we only have 6 electrons. So first we fill each orbital with just 1 electron based off of Hund's rule, and then we have 1 more left, so we pair it up. So we do have paired electrons in the d subshell, but we also have 4 electrons that are unpaired. All right, and so iron is not the right answer. Then we have cobalt. Cobalt is right here. It has 1 extra electron than iron. So instead of 3d6, it would have 3d7, and we'd have 1 more electron to put in here. But you notice, again, unpaired electrons here in that 3d orbital. So cobalt isn't the right answer either. Let's look at our last example, which is helium. Helium is right here. And the electron configuration for helium is really easy. It is just 1s2. And look at that. Helium has both of its electrons paired in the 1s orbital. This is the correct answer. So 5 is going to be D. Let's move on to problem 6. Problem 6 says an electron returns from an excited state to its ground state, emitting a photon at wavelength 500 nanometers. What would be the magnitude of the energy change if 1 mole of these photons were emitted? Now, when an electron transitions from an excited state to its ground state, it emits a photon with a specific wavelength. And the energy of this photon can be calculated using this relationship that E equals Planck's constant multiplied by the speed of light over wavelength. Here, H is Planck's constant. It's equal to 6.626 times 10 to the minus 34 joules per second. Joules times second, I'm sorry. And then the speed of light, we can approximate 3 times 10 to the 8 meters per second. And then the wavelength we're given is 500 nanometers, which is equal to nanometers, right? We talked about this metric prefix. Nano is 10 to the minus 9. So 500 nanometers is 500 times 10 to the minus 9 meters. So we have a lot of really good information here to figure out the energy of 1 photon starting off. So that's going to be our first step. We're going to use this equation, all right, to calculate the energy of 1 photon, or at least let's set it up here. All right. The energy is going to be equal to Planck's constant 6.626 times 10 to the minus 34 joules times second times 3 times 3.00 times 10 to the 8th power meters per second, all over the wavelength, which is 500 times 10 to the minus 9 meters. Notice we converted nanometers to meters because that way units cancel out since the speed of light is in units of meters per second. Now, this is for the energy of one photon. Our problem does ask for the magnitude of the energy change if we had 1 mole of these photons. So the way that we can compensate for this is by multiplying this by Avogadro's number. Avogadro's number is given to us in the problem at 6.02 times 10 to the 23 moles, all right, per mole. So what we can do is we can plug that in here as well. So let's write out our full equation now again. 6.626 times 10 to the minus 34 joules times second, 3.0 times 10 to the 8 meters per second, all over our wavelength of 500 times 10 to the minus 9 meters, now multiplied by Avogadro's number, 6.02 times 10 to the 23 inverse moles. Wonderful. Now, if you had the pleasure of having a calculator, this is an easy calculation just to plug into your calculator. If you're trying to do this speedy quick, all right, we can start to make some approximations here that can make this calculation a lot easier. So what we can first do is group. What we notice is that there's a lot of 10 to some power here in the numerator, right? These are all values that are in the numerator. So we can group these 10 powers together, and then we can group all the individual numbers associated with those 10 powers together. This is going to make it easier to kind of start to approximate things here. So now what we can rewrite is that energy is going to be equal to 6.626 times 3 times 6.02, and then that's multiplied by all of these 10 powers. So 10 minus 34 times 10 to the power 8 times 10 to the 23 power. All right, and then that's all over our 500 times 10 to the minus 9. Okay, now we can make some further approximations here. Let's approximate this number to about 7. This can stay a 3, and this we're going to approximate to 6. So now what we have is 7 times 3 times 6. All right, and we can do something really cool with these 10 powers. We can just sum up their exponents here. All right, minus 34 plus 8 plus 23 is going to give us minus 3. So now our 10 power can be simplified to just 10 minus to the power minus 3. And this is all over 500 times 10 to the minus 9. 7 times 3 is 21. All right, and then we can multiply 21 by 6 really easily. This is just a quick calculation here, 186. So now what we have is about 186, all right, over 500. And then now we're going to group these times these 10 powers here. So we have 10 to the minus 3 in the numerator, 10 to the minus 9 in the denominator. Okay, so far so good. Let's simplify these a little bit further, okay? This 186 over 500, let's just keep it that way for now. But this 10 to the minus 3 over 10 to the minus 9, all right, we can figure this out by doing a subtraction because they're being divided. They're not being multiplied together like we saw right here. So what we have here is now minus 3 minus negative 9, which is minus 3 plus 9, which is going to give us 6. So now we have 186 over 500 multiplied by 10 to the power 6. Okay, now we can figure out this approximately. All right, we're going to be a little bit lenient with the way that we do this approximation. 186 over 500, this is just a little bit over 1/4. If it was 125 over 500, this would be exactly 1/4. This is close enough. All right, this is about 1/4. So now what we have is 1/4, let's say approximately, times 10 to the power 6. Now, 1/4 is 0.25 times 10 to the power 6. If we move this decimal over here, now we have about 2.5 times 10 to the 5th power. Let's see if we have an answer choice that's close enough to this. And I'm sorry that our math kind of bled through the next problem, but we'll erase this up when we get to problem 7. So let's see if we have an answer choice that's close to 2.5 times 10 to the 5th. That's going to be really close here to answer choice D. So if you have the pleasure of having a calculator and you wanted to do quick math, you can plug this into the calculator. If you're trying to do this really quickly by doing some approximations, you can get pretty lenient with these approximations and still get an answer that's close to the options we have here. So the correct answer for problem 6 is going to be D. Wonderful. Let's move on to problem 7. Let's read problem 7 while I erase a little bit of this work that we just did so we have room. Problem 7 says, suppose an electron falls from n equals 4 to n equals 1. Which of the following effects is the most likely? A says a photon is absorbed. B says a photon is emitted. C says the electron moves into a p orbital. And D says the electron moves into a d orbital. All right, so when an electron transition between energy levels in an atom, it's either going to absorb or emit energy in the form of photons. The energy difference between the initial and final states determines the energy and hence the wavelength of the emitted or absorbed photon. So some key concepts to remember from our lecture while you're tackling this problem is when an electron moves from a higher energy level, an excited state, to a lower energy level, a ground state, energy is released in the form of a photon. When an electron falls, a photon is emitted, and the energy of the photon again corresponds to the energy difference between the two levels. When an electron, though, absorbs energy, in that case, it's actually going to move from a lower energy level to a higher one. Now, what's happening here is we're going from n equals 4 to n equals 1. So we're going from high energy level to low energy level. We're going to be emitting a photon. And actually, the correct answer here is B. A photon is emitted because it's going from higher energy level to lower energy level. And in that case, A is incorrect because a photon's only absorbed when you go from low energy level to high energy level. But let's also work through C and D and why those are not the correct answer. C says the electron moves into a p orbital and D says the electron moves into a d orbital. We're going from n equals 4 to n equals 1. When n equals 1, the only subshell that's available is the 1s subshell. And that's why C and D are not the correct answer. We're not moving into a p or d orbital. We're moving into an s orbital. And so the correct answer for 7 here is going to be B. Let's go ahead and move into problem 8. Problem 8 reads, which of the following isotopes of carbon is least likely? Now, isotopes are atoms of the same element that have the same number of protons, but they just differ in the number of neutrons. This results in different atomic masses. Carbon has several isotopes, only a few, though, are naturally occurring and stable. Now, recall that this superscript, if you're looking at these answer choices, this refers to the mass number of an atom, which is equal to the number of protons plus the number of neutrons present in an element. Now, according to the periodic table, carbon contains 6 protons, which means its atomic number is going to be 6. almost all atoms that have an atomic number greater than 1 have at least 1 neutron. So let's keep that in mind as we go through the answer choices. I actually want to start with B first. So carbon 12. This is the most common isotope of carbon. All right. It has a mass number of 12. So that means it has 6 protons plus 6 neutrons. Carbon 13. All right. This is also another isotope of carbon. It's less common than carbon 12. Carbon 12, by the way, it makes up about 98% of all carbon found in nature. This isotope carbon 13, it's about 1% of natural carbon. Here it has 6 protons plus 7 neutrons, hence why the mass number is 13. Then carbon 14, all right, this is less common, but it's possible. This is going to be 6 protons plus 8 neutrons. Now let's look at answer choice A here. It has a mass number of 6, and we know that carbon has 6 protons, which means for it to have a mass number of 6, it has 0 neutrons. This is not possible. And so this is the most unlikely form of carbon here. So which of the following isotopes of carbon is least likely? The answer is going to be answer choice A. Wonderful. Let's move on to problem 9. Problem 9 says, which of the following best explains the inability to measure position and momentum exactly and simultaneously according to Heisenberg's uncertainty principle? Now, the Heisenberg uncertainty principle is a fundamental concept in quantum mechanics that was formulated by Werner Heisenberg in 1927, and it states that it is impossible to simultaneously measure both the position and momentum of a particle with infinite precision. The more precisely that one of the properties is measured, the less precisely the other can be known. And this is expressed mathematically here. This is the uncertainty principle where delta x, this is the uncertainty in position, delta p is the uncertainty in momentum. Here, this h bar, this is Planck's constant, but it's a reduced Planck's constant. H bar is Planck's constant h divided by 2 pi over 2. Now, the explanation of this principle, well, this principle arises from the wave-particle duality of quantum objects. Particles, they exhibit both wave-like and particle-like properties, and the wave nature of particles means that there is an inherent limit to how precisely we can define their position and their momentum. Now, this is not due to limitations in our measuring instruments or our definitions of units, but it's just a fundamental property of quantum systems. Now, with that refresher, let's go through this answer choice by answer choice. A says, imprecision in the definition of the meter and kilogram. This option is incorrect because the uncertainty principle, it's not due to imprecise definitions of units. It's a fundamental property of quantum systems. So A is not the correct answer. B says, limits on accuracy of existing scientific instruments. This option is also incorrect. While measuring instruments do have limits, the uncertainty principle is not due to instrumental limitations. It's more of a fundamental characteristic of particles just at that quantum level. So B is also incorrect. C says error in one variable is increased by attempts to measure the other. This answer choice is correct. Remember that the Heisenberg uncertainty principle states that increasing the precision in measuring one property inherently increases the uncertainty in measuring the other property. And this reciprocal relationship is a fundamental property of quantum mechanics. C is the correct answer. Let's still go through D though. D says discrepancies between the masses of nuclei and of their component particles. Now, this option is incorrect because it tries to relate the nuclear mass and binding energy rather than relating back to the uncertainty principle. So D is also incorrect. The correct answer for 9, again, is going to be answer choice C. Let's go ahead and move into problem 10. Problem 10 says, which of the following electronic transitions would result in the greatest gain in energy for a single hydrogen electron? A says an electron moves from n equals 6 to n equals 2. B says an electron moves from n equals 2 to n equals 6. C says an electron moves from n equals 3 to n equals 4. And then D says an electron moves from n equals 4 to n equals 3. Now, for an electron to gain energy, which is what this problem is asking, it has to absorb energy from photons to jump up to a higher energy level. This actually helps us eliminate answer choice A and D, because what's happening here is that the electron is moving from a higher energy level to a lower level one, which is going to result in emitting a photon that results in losing energy. That's not what this problem is asking. This problem is asking what would result in the greatest gain in energy. So we're looking for a transition from low to higher energy level. So that leaves us with B and C. Now, B says that electrons moving from n equals 2 to n equals 6, and C says an electrons moving from n equals 3 to n equals 4. There is a bigger jump between n equals 2 to n equals 6 than there is between n equals 3 to n equals 4. And so just based off of that, we can conclude that the correct answer here is going to be answer choice B. Now, you can further confirm it by plugging it into an equation, but it was a really easy problem just to work through logically, so we don't really have to overcomplicate this kind of problem. With that, let's go ahead and just move into problem 11. Problem 11 says, suppose that an atom fills its orbitals as shown. Such an electron configuration most clearly illustrates which of the following laws of atomic physics. Is it Hund's rule, Heisenberg's uncertainty principle, Bohr's model, or Rutherford's model? Now, the given electron configuration diagram, it shows the filling of electrons in the 3s and 3p orbitals. Each box represents an orbital, and each arrow represents an electron with its spin. And the configuration indicates how electrons are distributed among available orbitals in an atom. Now, to determine which law is illustrated by this given configuration, we need to remember and understand the principles that govern electron distribution. Hund's rule is an important one in that. Hund's rule states that electrons will fill degenerate orbitals of the same energy singly as far as possible before they pair up. What this does is it minimizes electron-electron repulsion within an atom. Now, in this diagram, the 3p orbitals are filled one electron at a time in each orbital before any orbital gets a second electron. So this is a clear illustration of Hund's rule. And the correct answer here is, in fact, A. Now, B says Heisenberg's uncertainty principle. Remember that this principle just states that it's impossible to simultaneously know both the exact position and the exact momentum of an electron. So it deals with the inherent uncertainties in quantum measurements, not the arrangement of electrons in orbitals. So B is not the correct answer. C says the Bohr model. The Bohr model describes electrons in fixed orbitals or orbits around, the nucleus with quantized energy levels. While important historically, it does not explain the detailed arrangement of electrons within subshells S, P, D, F, so on. So C is also not the correct answer. Rutherford model, this describes the atom as having a dense nucleus surrounded by electrons, and it does not provide any details on electron configuration within energy levels. So this is far away from being the correct answer. So in short, the correct answer to problem 11 is going to be A, Hund's rule. Let's go on and move into problem 12. Problem 12 says how many total electrons are in a cesium cation, and here we are given the mass number. Now, to determine the number of electrons in a cation, let me just refresh your memory of a couple of things. First, the atomic number of an element, this is going to be equal to the number of protons in its nucleus, and it's also equal to the number of electrons in a neutral atom of that element. Then for cations, well, a cation is formed when an atom loses one or more electrons, and the charge of the cation indicates how many electrons have been lost. Now, we're just told cation with no extra additional information, so really what this means is a cesium plus cation, which means it has lost one electron. Now, to answer this problem, let's first figure out the atomic number of cesium. So we can look at the periodic table of elements and we'll figure out that cesium has an atomic number of 55. This means that a neutral cesium atom has 55 protons plus 55 electrons. But this is a cation and it has a plus charge, which means that the cesium atom has lost one electron, which means we take this number of electrons, we're going to subtract one from it to get a total of 54 electrons. Therefore, the total number of electrons in this cesium cation is going to be 54, and the correct answer here is going to be A. Wonderful. Let's move on to problem 13. Problem 13 says the atomic weight of hydrogen is 1.008 AMU. What is the percent composition of hydrogen by isotope, assuming that hydrogen's only isotopes are hydrogen and deuterium? Hydrogen has one proton and one electron. Deuterium has one proton, one electron, and one neutron. To determine the percent composition of hydrogen by isotope, we have to understand the concept of atomic weight and how it relates to isotope composition. The atomic weight or atomic mass of an element is the weighted average of the masses of its isotopes based on their abundance. So we have a lot of good information here to figure this out. We know that the atomic weight of hydrogen is equal to 1.008 AMU. Now, we also know that we have two isotopes of hydrogen. I'm going to refer to them as 1H and 2D. We know the atomic mass of both. The atomic mass of 1H is 1 AMU, and the atomic mass of 2D is 2 AMU. Now, to set up this problem, we're going to let X be the fraction of 1H, and we're going to let Y be the fraction of 2D, and these fractions of each isotope have to sum up to 1, in other words, to 100%. So we can write that X plus Y is going to be equal to 1. Now that we have that, we can also write the atomic weight expression for hydrogen. And this is something that we talked about in our background information video. We know that the atomic weight of hydrogen is 1.008 AMU, and that's going to be equal to the fraction of 1H multiplied by the mass of 1H plus the fraction of 2D multiplied by the mass of 2D. And so now what we can write is that 1.008 AMU is equal to X multiplied by 1 AMU plus Y multiplied by 2 AMU, since we know the atomic mass for 1H and 2D. Now, something else that we want to do is we don't want to have two unknown variables. We'd rather just have one that we can solve for. So what we're going to do is we're going to use this expression to redefine a variable. What we want is a definition for X, all right, that we can redefine. So what we're going to do is we're going to write Y is going to be equal to 1 minus X. And we just get this by subtracting X from both sides. So now we know that Y is equal to 1X. We're going to replace this Y with 1X. And so now our expression reads 1.008 AMU is equal to X, that's X times 1, plus 1 minus X multiplied by 2. 2. And now this becomes a really easy expression to kind of distribute and then solve. What we have is that 1.008 AMU is equal to x plus 2 minus 2x. All right, and we can rearrange this, and what we have is then 1.008 AMU is equal to 2 minus x. All right, and then we can just solve for x by moving x to this side and then moving 1.008 over here. All right, and so we get x is equal to 2 minus 1.008. X is equal to 0.992. And now that we have x, we can actually just go ahead and plug this back into this equation to figure out y. So y is just 1 minus 0.992, which is going to give us 0.008. All right, and so now we can convert these two percents by just multiplying by 100%. And so x is going to be equal to 99.2% and y is equal to 0.8%. And this is x is our percent for hydrogen and y is our percent for deuterium. And that makes the correct answer for problem 13B. So 13 is B. Let's go ahead and move into problem 14. 14 says, consider the two sets of quantum numbers shown in the table which describe two different electrons in the same atom. Which of the following terms best describes these two electrons? Now, the term in the answer choices, parallel, opposite, anti-parallel, and paired, all refer to the magnetic spin of the two electrons. So that's where we want to look, all right, at the ms value. The quantum number ms represents this property as a measure of an electron's intrinsic spin. These electrons' spin are parallel in that their spin are aligned in the same direction because both of their ms value is plus 1/2. So again, both electrons have the same spin quantum number, plus 1/2, indicating that their spins are parallel. And the term parallel in this context means that the electrons have the same spin orientation. And so the correct answer for 14 here is going to be answer choice A. Let's move on to our last and final problem here. Problem 15 says, which of the following species is represented by the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. And what we have here are a couple of answer choices that are given to us, all right? And we're going to work through each single one. So the first, statement 1, chromium, and it looks like it's neutral. There's no plus or minus, so it's not an ion. Then we have here manganese plus, so this is a cation with one less electron. And then we have iron 2 plus here. This is also a cation. Iron has lost 2 of its electrons. So what we're going to first do is we're going to start off with chromium. Chromium here is neutral. It's not an ion. So let's just go ahead and figure out the electron configuration for chromium, which is right here on the periodic table. Let's read off the electron configuration from the periodic table. We have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3D, 1, 2, 3, and 4, 3D4. Now, chromium, this is really interesting. This was one of the exceptions we talked about. Due to the stability of the half-filled d orbitals, neutral chromium is actually assumed to have an electron configuration instead of 4s1, 3d5. This was one of the exceptions we talked about. And so actually, the electron configuration for chromium matches with the one that is given to us in the question stem. So chromium indeed does have this electron configuration. So statement 1 is correct. Now let's do statement 2, manganese. And this is a manganese cation, so a manganese plus. It's lost 1 electron. Let's figure this out. So let's go ahead and figure out the electron configuration for manganese, all right? The neutral manganese atom, all right? The manganese is right after chromium, so it actually has one additional electron. So we're just going to go ahead and write it normally as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. All right? So this is the electron configuration for manganese. But now, this is a manganese cation. We just wrote the electron configuration for neutral manganese. It loses one electron to form this manganese cation. Where is it going to lose that electron? It's going to lose that electron from the 4s subshell according to the rule that the first electron removed comes from the highest energy shell. So it's actually going to lose that electron from the 4s subshell. And so manganese plus its electron configuration is actually 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. This electron configuration also matches with the electron configuration that's provided in the question stem. So statement 2 is also correct. Now we need to figure out the electron configuration for iron. All right, just neutral iron, and then we're going to figure out what the iron 2 plus cation electron configuration is going to look like. So let's figure out the electron configuration for neutral iron. We figured this one out earlier, so we can just rewrite it. 1s2, 2s2, all right, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6, 3d, 6. Now, here, it's going to lose 2 electrons because it's an iron 2 plus. Where is it going to lose those 2 electrons from? Again, according to the rule, it's going to be removed from this 4s subshell. And so then the electron configuration for Fe2 plus is 1s2, 2s2, 2p6, 3s2, 3p6, 4s0, 3d6. This electron configuration doesn't match with the electron configuration provided from the question stem. So statement 3 is incorrect. Only 1 and 2 have the same electron configuration as provided by the question. And so the correct answer here for problem 15 is going to be answer choice B. And with that, we've completed all the problems for this problem set. Please let me know if you have any questions, comments, or concerns. Other than that, good luck, happy studying, and have a beautiful, beautiful day. Future doctors.